Hello and welcome to my YouTube channel. This is Dramani Online Mathematics, and today we are going to look at the exact differential equation, but we have to start with the total differentials first, then that will lead us to the exact differential equation. Alright, so now for us to start with this, let's look at something like this. Let's assume that I have u of x, y. Let's say I have something like this. This means that this function u is in terms of x and y. So if I want to differentiate this, then I'll have to differentiate partially. I cannot, once I have two variables here and I want to differentiate it, I have to differentiate it partially in terms of x, then partially in terms of what, y. And when I'm doing that, this is what I'm going to get. The u is equals to partial derivative with respect to x dx plus partial derivative with respect to y dy. This is what we call delta. So delta u, delta x, delta u, delta y. This is how it goes. Is that okay? So anytime they give you something and they ask you to find the total differential, or show whether it's a total differential or something like that, what you do is that you take the partial derivative with respect to what, x, then you attach the dx to it. Partial derivative with respect to y, you attach what, dy to it. Remember that this is delta u and this is d, so they are not the same. Is that okay? Now let's look at example. This is an example. This is an example. We have determined the total derivative differential of the equation. So once they just says the total, this is the formula we are going to use. And here, the partial means that you are differentiating with respect to x. So at that point, anything that is y there becomes what? Constant. Anything that is y becomes constant. And the one with respect to y, the partial with respect to y, means that anything that is what with x also becomes what? Constant. So when you are dealing with y, x becomes constant. When you are dealing with x, y becomes constant. That's the meaning of the partial derivative. We are going to use that partial here, so take note of it. Make sure you subscribe for me, please. That one is very, very important. Okay, so now let's look at the first example. My board is too small. So the first example is saying that we should find the total differential of this. Okay, so per the formula that was given, first you need to find the partial derivative with respect to what? X. So as I said, with respect to x, all the y values becomes what? Constant. So this is constant. So when you are, when you are differentiating and there's a constant, and that constant is multiplying a variable, you don't do anything to the constant. You just differentiate the variable, and whatever coefficient that comes in there, you multiply by the constant. So that's what you're going to do. So when I differentiate x cubed, that one is given as 3x squared. Then my constant, I maintain it, y squared. Is that okay? Then I come to this place. The x here, if I differentiate x, I'll get 1. So it will leave 2 times 1 times 1. That will still give us 2y. Then this place, if I differentiate, alright, this side is y. If I differentiate x squared, I'm going to have 2x. Okay, now if I differentiate 2y, this one is with respect to x, so if I differentiate 2y, that will give me 0 because y is constant, 2 is constant, so that gives me 0. Then I'll then come and take delta u delta y. So at this point, everything of x goes to constant. So when I come to this place, this x is constant, so you leave it y squared. So if I differentiate y squared, that will give me 2y. So I have 2, but I'll bring my constant first, y, plus, if I differentiate y, leave it 2x, but if I differentiate y, that will be 1. So that gives you 2x. X squared will go to 0 because you are differentiating partially with respect to x. So everything, with respect to y. So everything of x goes to 0, leaving this one. If I differentiate 2y, you know that will give us 2. So this is the two things that we have here. Is that okay? Now, let me clean the question. I'll write it if the need arises. Now after this, you know that the formula is giving us du equals delta u delta x dx plus delta u delta y dy. So du is equals to, so now delta u delta x is this one. So that is going to give us 3x squared y squared plus 2y plus 2x dx, okay, plus then delta u delta y is also having 2x cube y plus 2x plus 2 dy. So this is what we call the total differential. The total differential. Okay, so now let me look at the second example. Where you have u of xy equals sine xy plus 2x plus 3. So first thing I have to find delta u delta x. Now delta u delta x means that I'm going to focus on the x, so y becomes constant. So if I differentiate sine x, so forget about this y. If I differentiate sine x, you know, if you are differentiating something like sine 2x, it's a matter of differentiating the x. If you differentiate x, what do you get? You have x, 1. So if you differentiate sine x, that will give you cos x. Then you bring the 2 out. Is that okay? So the same thing that we are going to do here. So looking at this one, if I differentiate sine x, I'll get cos x. Then the y comes out. So y cos xy. I hope you understand that. This is how you do. It's a composite function. So it's like you differentiate the whole function. That will give you cos. Then you come and pick the inside one, then you differentiate. Then you multiply by it. That's all. Then this side will give us what? 2. This goes to 0, right? Then you also have delta u delta x. So looking at delta u delta x, delta y, this side is going to give us x cos xy. Then here will be 0, here will be 0 because there's no y here, there's no y here, so they all become constant, so they all goes to 0. So my final answer will be du equals the partial derivative of this, which is y cos xy plus 2 dx plus x cos xy dy. So that becomes the total derivative of this. So you see how we find the total derivative, and you see how the partial works. So when the partially goes with x, then like when you are taking partial differential with respect to x, then anything else becomes constant. Yes, with respect to y, anything else becomes what? Constant. Very good. Now let's proceed to the next one. Okay, so now let's look at this. This is what we just finished solving. Okay, the first example. This is what we had. Now, if we let m of x, y, so this is a function of m in terms of x and y, to be equals to the first one, which is 3x squared y squared plus 2y plus 2x, and we let n to be equals to x, n in terms of x, y, that's a function of x and y, to be equals to the other side, which is 2x cube y plus 2x plus 2y. Okay, now when we have something like this, then you can conclude that my du equals, now the whole of this is m in terms of x and y dx, and the whole of this one is now n in terms of x and y dy. Have you seen it? Very good. Now that we are having this, if it's this to 0, that is m in terms of x, y dx plus n in terms of x, y dy to 0, then you can say that du is equals to 0. Is it right? Yes. So now with this, let's take integral for both sides. If you integrate this, you have what? U. If you integrate a constant, that will still be a constant, so a 0, right? If you integrate 0, you get 0 plus a constant, so c. So you can say that u is equals to what? C. So now this one can be written as u x y equals what? C. Meaning that after getting our solution, when we get to the solution side, after getting our solution, we will always equate it to what? C. We will always equate it to C. Also take note of this one. Always the m is attached to the dx, and we had it from this place, and then n is also attached to what? The y. Have you seen it? And if you look at this one, we have something like this. Du equals delta u delta x dx plus delta u delta y dy. So there is this one that the delta u delta x was replaced by m y, then delta u delta y was also replaced by n x y. So take note, all these things you will start using it when you get to the solution to the exact differential equations. Now let's look at criteria for exact differential equation or exact equation. At which point can we say that this equation is exact? Let's look at the criteria for that. If you look at this one, at which point can we say that this one is exact differential or exact equation? The only way to know is that when I take the partial derivative, that's delta m, with respect to delta y, when it's equals to delta n with respect to delta x, when the partial derivative of this is equal to the partial derivative of this, here with respect to y, here with respect to x, then we can say that this is what? Exact differential equation. Okay, so now let's look at how to solve something like this, or how to verify it. At the point where this is not equals to this, like this, if I have delta m delta y not being equals to delta n delta x, then this cannot be considered as what? The exact differential equation. But when it's equal, then you can consider this as what? Exact differential equation. So now let's look at an example. Okay, so now let's look at this simple example. Verify the exactness of the differential equation. So you want to verify if indeed this one is a differential equation. Yes, it looks like an differential equation, exact, but you cannot just look at it and guess that this is that. You have to verify. So we are saying that the one that is attached to the dx always go for the m. So we can say that m in terms of x, y is equals to 2x minus 4y plus 5. Okay, so now we take the partial derivative of m with respect to y, and when you do that, I've already explained to you, once you are going with respect to y, any other thing becomes constant. So when I differentiate the whole of this becomes constant. When you differentiate constant, what do you get? You have 0. Then when you differentiate this 5, also giving you 0, so you have negative 4y. If you differentiate 4y, that will give you negative what? 4. Good. Now let's also pick this side, which is the n xy equals. Now there's negative here, so this negative has to be there. So even if I multiply the negative through, I'm going to have negative 4y positive 4x. I'm going to have negative 4y plus 4x. Then I take the partial derivative with respect to x. So with respect to x, this will give me negative what? 4. Positive 4. Why are you saying that it will give us positive 4? Because here with respect to x, so anything here or anything that contains y become constant. So this side become constant, leaving only the 4x. If I differentiate 4x with respect to x, I have what? Only 4. Now let's compare the two. The first one I have negative 4, the second one I have positive 4. You realize that delta m delta y is never equals to delta n delta what? X. So we can say that hence the equation is not what? Exact. So this one is not exact. So this is how you prove for exactness. First thing, you have to be able to know this one and that one. If you mistakenly replace this one by n and here by m, there will be a problem. So make sure that you do not forget where the m is and the n is. Then after doing that, you take the partial derivative with respect to y and with respect to x for both. Then the answers you compare, if they are the same, then you can conclude that it's exact. If they are not the same, then you cannot say that it's what? Exact. Now let's move to the next example. Okay, so now let's look at our number 2 or example 2. We are saying that to verify the exactness of this differential equation. So we want to see whether it's an exact. Yes, simple as that. Now, this is very simple. But before you do this, you have to make it look like how the general one is. So first thing, you have to change this one to x plus y squared dy dx plus y equals 0. Then you multiply through by the LCM. So here the LCM here is dx, meaning that if I multiply through, this side will be x plus y squared dy plus y dx equals 0, because 0 times the dx will still be 0. Now looking at this one, can write it well as y dx plus x plus y squared dy equals 0. So this one, the one that's attached to the dx, is always what? For the m, and those that are attached to the dy is always for the n. Is that okay? Meaning that my m in terms of x and y is equals to y, and my n in terms of x and y is equals to x plus y squared. So first I take the partial derivative of m with respect to y, and that will give me 1. Then I'll take partial derivative of n with respect to x, and that will also give me 1 because the y side goes to this thing. Now you realize that delta m is equals to delta n delta x, which is equals to 1. Hence, since the delta m delta y equals delta n delta x, since they are equal or they are all equals to 1, then we can say that this particular question given is an exact. Is that okay? And you realize, or you have seen how I change it from this side for it to look like this first before I started solving. So when they give it to you, you don't just look at it and be doing what you want. Is that okay? Very good. Now let's move on to last example, and that example I'll give it to you as a try work so that at your leisure time you do it.
Okay.
Alright, so now this the try work. Verify the exactness of this. So 2xy dx plus x squared minus xy dy equals 0. So you have to verify it. Please try to subscribe and share the link to your friends, and also like and leave any comments that you think or any problem that you have in the comment section. Thank you very much.